So this week we're going to start talking about water vapor. It's a very interesting term, the way we use it in the atmosphere, all the water that comes in. You ever think about it? We drink really distilled water in the sense that we don't have salt in it. And most of the water on Earth comes from the oceans, which are very salty. So it's a good thing that the water cycle works the way it does. We could be very, very thirsty. Uh, Right here is an image of mid-level, which is around 700 millibar water vapor. So you can see here tons of water down in the western Gulf of Mexico. Uh, some little circulation here of water. And look at all up at the east coast here and across the Great Lakes up here. And interestingly, this plume of water is originating all the way out off the Pacific coast, off of Mexico. So lots of moisture in the eastern half of the United States currently with this. I wanted to also show you another thing, precipitable water. Precipitable water simply is the amount of water that you could get wherever you are if every bit of water condensed into rain. So with that being said, notice how much higher precipitable waters are, like over 1.5 to 2 inches in the everything east of the Mississippi. And that's why there has been a lot of heavy rain there. Look at along just off the east coast and over Florida and stuff. It's well over 2 inches, almost 2.5 inches. That is extremely high precipitable water for the United States. So that's what we're dealing with right now. Not a lot of precipitable water out in the West Coast necessarily, but boy, there is on the eastern part of the United States right now. Also down here along the tropics, where you would expect a lot of water, there is. So let's learn a little bit now about all of what I've just been talking about and showing you. So we're going to talk about humidity, saturation, and we're going to get into some stability. So with that, let's start from the beginning here. And one of the things, interestingly, is we call them atmospheric rivers. They transport a tremendous amount of water, usually from some ocean to the land. This is just a one over the Pacific Ocean, striking the Pacific Northwest. And you can see the bright all the way across the Pacific, almost out into Australia, where the moisture is originating. I showed you some of those in that one picture where I showed you the moisture coming up out of the southeastern Pacific there and up across into the northern part of the United States. That is a typical plume of moisture, not as concentrated maybe as some atmospheric rivers, but still a decent push of moisture. You can see atmospheric rivers can come in, hit land, get lifted up, cause rain, may hit a higher precip over bigger mountains. So the total amount of water in the atmosphere is really, really small. And most of it's all confined to the troposphere. And generally, if all the water vapor were removed from everywhere in the atmosphere, you get about 1 inch depth of water over the globe. So we're going to learn now where all this water comes from and how it gets recycled back through the water cycle here a little bit. So much of Earth's water is in the oceans, 96.5%. And other saline water is another 0.9. So that leaves just fresh water as being only 2.5%. That's in the ground or in the glaciers. So you can see how the water starts out in the oceans, winds up going here, winds up being used by man, really, through all of these different other melting processes and everything. Here is a very typical water cycle. The water evaporates over the ocean. Evaporation is the first thing that occurs, and the sun controls that. So it evaporates over the ocean, rises up, condenses into precipitation. and falls back down. Some of it falls into the ocean. Other of it may wind up being put over mountains or over cold fronts or warm fronts and falls onto the land. Now, land can be a big factor in how that rain precipitation moves. Some of it may go into ice and snow and stay on the mountaintops. Out in California and all, they love a good snow season because it allows them, all that moisture gets trapped on the mountains and then it takes a while for it to melt down. So that all helps out. Uh, in the land now, we may have things like mountains that allow the moisture to come down along the side of the mountain very quickly, or we may have flatlands, or even things like farms and all that have a lot of evaporation as well off of the plants. They send a lot of moisture into the ground. Eventually, a lot of this moisture can flow back into the oceans through the rivers, and some of it winds up being stored in the ground. We have groundwater. We have wells that dig down into the ground, pump up that water, water plants, help us drink water. So the water is the one thing that changes state in the atmosphere. And how does it do that? It does it through evaporation, condensation. Transpiration is coming out of the water, taken up by roots of plants, sublimation, and deposition. All of those contribute in some manner or another to how much precipitation is going to fall. So here is the amount of water that comes from the ocean, evaporation, 426,000 cubic kilometers per year. 368,000 cubic kilometers rain back on the ocean. So we've lost some. Then precipitation on the land, another 114, evaporation from the land, and we have a net gain by the land of 40,000 cubic kilometers, and that flows either from the rivers and streams or becomes part of the groundwater supply, which does eventually flow back into the ocean. So here you have the total budget of all that water that's out there and how it works. So humidity describes the amount of water vapor in the air. Some days it is really, really humid and uncomfortable. Other days in the winter, very, very dry. So we want to be able to measure this. We have different terms. We're going to go through those. So vapor pressure. Well, water vapor is a gas. We learned that every single gas has a pressure, a total air pressure it contributes to. So water vapor or vapor pressure is that pressure of the water vapor in the atmosphere. The volume-wise, interestingly, only about 4% in the lower mass and lowest kilometer may be that water vapor. And that's really on a very, very humid day. Another one, mixing ratio. So that's the mass of that water vapor per mass of the remaining dry air. So what we've done is taken a parcel of air and we said, oh, we got this much water vapor in it. What's left must be dry air. That ratio then is the mixing ratio. So what we have done is subtracted out the water vapor that was in that air parcel and left just the dry air so the two relate to each other. That gives a mixing ratio. Specific humidity, on the other hand, is the mass of water vapor compared to the total mass. So they're generally not going to be a lot different, but they are slightly different. And finally, absolute humidity, the mass of unit of volume here. So when air reaches saturation, in other words, when the same amount of molecules are condensing as are evaporating, it has reached the saturation point. Or at that point, we're saying we have the air is saturated. It is changing That number where it becomes saturated changes constantly. But when we talked about vapor pressure or mixing ratio or any of the other ones, we just add the word saturation to them and we get the amount of water vapor compared that would be needed to saturate the air. And interestingly, air temperature changes this. The hotter the air is, the more there's kinetic energy, the tougher it is for water molecules to condense. So hotter air holds more water. That's why in the summertime, when it feels humid, it is very humid because there's a tremendous amount of water in the air. Wintertime, when it's really dry, there's not much water vapor in the air. And you can see here the saturation vapor pressure and how it increases very, very quickly. The further up you get, the hotter it gets. Starts off, minus 40 to 0, slight change, 0 to 20 degrees Celsius. It's starting to pick up. And from there on, it becomes much, much more moisture needed. So relative humidity is our most useful term. We're all familiar with it. When you hear it on TV, look at your weather apps. They're going to say, oh, the relative humidity right now is 35%. Oh, the relative humidity right now is 100%. It is simply the whatever mixing ratio, vapor pressure, compared to the saturation one. The closer they are to each other, the better chance the air is completely saturated and condensation is occurring. That's at 100%. So if the temperature and pressure are constant, then the amount of water vapor must be changing to change the saturation. If one or the other changes, however, they may directly impact relative humidity as well. So let's take a look at a typical day. We're not bringing any moisture into this atmosphere. No advection of moisture whatsoever. In the morning, temperatures drop after sunset, fall off some more. What happens is the relative humidity goes up. Matter of fact, it may reach 100%. You may have fog in the mornings. So that is because the air can't hold as much moisture. Now, sun comes up, starts heating the air can hold more moisture. So relative humidity starts down. And by late afternoon, the relative humidity will be at its lowest typically, where we haven't added any moisture whatsoever to this air. So you get the lowest relative humidity when the temperature is highest. And then the whole process just repeats. The things that will change this are adding moisture to it. So dew point. Dew point is what we've been talking about on surface weather maps for a lot since you started this course. And dew points are very simply the air temperature must cool to that level to reach saturation at a constant pressure. In other words, pressure didn't change, so we cooled down and down till we reach saturation. The difference between the dew point and temperature, you can calculate the relative humidity from that. The further apart they are, the drier the air. The closer they are to each other, the closer they are to saturation. When it's raining, many times, the dew point and temperature may be exactly the same. Here you can see the change in dew point between winter and summer. Notice, in winter, dew points a lot of times are less than 20 degrees Fahrenheit. However, in the summertime, notice dew points gets up into the 60s, even 70s over a lot of the eastern United States. And for a while here, my dew points, at least at my house, have been in the 70s. Sometimes dew points can be in the low 80s, especially where evapotranspiration is occurring. Sometimes in the Midwest, you'll get that low 80 dew points only because, yes, there's lots of moisture in the air, but you add a little bit more moisture from the plants and it pushes the dew points up. Interestingly, in Oklahoma, when they cut the winter wheat, dew points drop by almost 15 to 20 degrees just because they've got rid of the evapotranspiration. Precipitable water, I showed you, highest is always going to be where the air is most warm, which is typically near the equator, and dropping after that. However, air can surge north from the tropics, this moisture, and come up into our area or other areas of the country and produce a lot of rainfall at that time. When you start seeing precipitable waters inching up over 1.5 inches, 2 inches, that is a tremendous amount of moisture, especially when you think of it as being advected in. So it's a continual stream of that much moisture coming in, causes tremendous rainfall rates sometimes. So how do we measure all this? We use something called electrohygrometer, which can look at the chemical changes and determine how much moisture is in the air. These are all used at all the ASOS sensors around the country at the airports, or AWAS at other small airports, and people get them in their backyards and all too as well. I showed you satellite images looking at the infrared imagery. If we know a specific wavelength, interestingly, we can figure out what that moisture is based on certain wavelengths. Certain wavelengths are from the mid, where I was showing you 700 millibars, others lower level, others are higher level. So it's interesting that the wavelength can help us detect where the moisture is and how much there is. And here you can see different water vapor plumes and all of these. So air, when it becomes saturated, forms clouds. So how the heck do we get a cloud to form then? Well, the air has got to cool or it doesn't become saturated. You're not going to probably advect enough air in to saturate it. So if the air is, as the air is cooled, that saturation vapor pressure decreases. So if the actual vapor pressure remains the same, at some point saturation occurs, we wind up with a cloud. So remember, air expands when it's rising. That means it's doing work, it's cooling. When that happens, you wind up with this saturation getting lower and lower till you finally form. So with all of this, it causes something interesting to happen. We can learn about atmospheric stability. You've learned that the atmosphere can rise, air can rise up, air can sink at a steady rate. Well, we're going to mess all that up a little bit here. Air can actually accelerate up or accelerate down based on stability. So how do we get an air parcel to be stable or unstable? All right. The air going up has a lapse rate or a change in temperature with height. Typically, right around 7 degrees, we'll say, might be the actual lapse rate for 1,000 meters. That means that if the air was dry, as it was rising up, it's cooling at 9.8, so it's cooling faster than that lapse rate. That means it's all, even if it got pushed up, it's still going to wind up being significantly cooler. And the cooler it gets, the more dense it gets, the more it's going to want to sink. And eventually, it will sink back down to where it started. And it will accelerate as it's sinking. That's stable air. However, we're pushing a particle of air up. It now becomes saturated. I just said we had 7 degrees lapse rate. Well, that parcel of air now is saturated. It's cooling at 6 degrees. So in 1,000 meters, it has gained one temperature warmer, 1 degree Celsius warmer than the surrounding air. So instead of wanting to sink, it's going to want to rise. And it's not just going to want to rise slowly, it's going to get faster and faster the more that temperature change difference is. So that is where you're going to get, we're talking about thunderstorms later, where the air is going to be able to rise so quickly. So that is instability and stability. Here you can see just what I talked about, depending on how the air parcel is moving. stable air, unstable air. So temperature profiles of the ambient air will change due to air mass advection, to cloud cover, maybe mountains. All of that can change the air profiles. So air is absolutely unstable if the air parcel is dropping more rapidly without it due than the dry adiabatic collapse rate. Or, so that would mean like if you were dropping at like 10.5 degrees Celsius per 1,000 meters. It doesn't happen in the normal atmosphere. But conditional instability does. And that makes a big difference in our forecast. So air layer stable for unsaturated and unstable for saturated. Neutral air, a rising or descending air parcel has the same temperature as its surroundings. So it's just moving at a steady pace up or down. We talked about Stubby diagrams earlier. I showed you some in a video earlier. All they are, temperature is down on the bottom, pressure or altitude is on the left. So all you're doing is plotting a dew point and a temperature on this curve. So if I wanted to say a dry adiabatic lapse rate, then I would always be plotting, oh, the temperature at the surface is this. 1,000 meters up, it's going to be 9.8 degrees colder. 2,000 meters up, it's going to be 9.8 degrees colder from the previous one. And we just plot that. That's why it curves to the left sharply. If it's a moist adiabatic, all I'm going to say is, oh, here it's 6 degrees warmer. Now it's 6, another 6 after that. And we can take an air parcel, we can project it along that path, and we can see how the temperature changes. And we can use then on the saturated air parcel and see how the air parcel impacts where that temperature is going to actually be. So some lifting mechanisms, obviously the air is heated, warms up at the bottom of the earth. It gets warmer than the surrounding air. It begins to rise. That's called convection. Fronts, warm fronts, cold fronts, both of them lift the air up. Once you get the air rising, we're getting that cooling process, which may form clouds. Orographics, mountains, great for forming things. Lifting condensation level, you're going to see this come up sometimes. It's the height at which a rising air parcel becomes saturated in clouds form. Mountains, you can get a lot of rain on one side of the mountain and nothing on the other. Interestingly, in West Virginia, this happens. If you have an east wind, the west side of the mountains gets much less rain than the east side of the mountains. And finally, convergent winds. These are winds that are coming together. I had one go through here yesterday morning. The air was converging along a very weak front, but it produced torrential rain for a couple of hours in the morning. So I hope you got a little bit out of this and let me know what you think.